Welcome to Chapter 5, Pure Mathematics Year 2, and in this chapter we're going to look at radians. Radians are a new measure for angles. So you can see the first objective here, we're going to learn how to convert between degrees and radians. There's a few things you need to know in advance. You're going to need to remember a little bit of trigonometry from GCSE and the work you did on trigonometric ratios, trig identities and equations from chapter 10 in year 1. I've also included a definition you'll be familiar with from GCSE. The definition is for finding the arc length and the area of a sector. And we're going to be using this and adapting it later on in the lesson. So without further ado, please pause the video and could you try the 4 warm-up questions on your sheet? All right, and let's have a look at the solutions. Okay, so today we only have 3 questions, which is a bit unusual. We normally have 4. And the first question is slightly different from what we're used to. We're going to look at an object traveling at 30 kilometers per hour, this object P, at a constant speed. So you'll be forgiven for thinking this is a mechanics question. It's not. What I've asked you to do is to write 30 kilometers per hour in this form, whereby 30 kilometers is what is equal to 1 hour, or every hour you travel 30 kilometers, which is essentially what it means. And to rewrite these units using different compound units. And as you can see, the first part of the question, we have to express 30 kilometers per hour as 30 kilometers per second. Okay, let's do this. So we'll follow the instructions and see where it takes us. So I'm going to write 30 kilometers as equal to 1 hour. All right, now if you look at the question, which part do we need to change? It looks like, well, the kilometers is fine, but we've got this measurement in seconds here. So I need to change the hours into seconds. So you need to recall a bit of knowledge here. So let's just make a note. We know that 1 hour is equal to 60 minutes. Okay, that's the first thing. And then to change the minutes into seconds, we know that's 60 seconds per minute. So it's 60 times 60, which is 3,600 seconds. Just be careful when you're multiplying 60 by itself. Okay, it's 3,600. Sometimes people write 360. So just double check that on your calculator if you need to. Okay, great. So now I can replace the 1 hour here with 300 seconds. So that's my next step. Let's write it out. So therefore, 30 kilometers is equal to 3,600 seconds. Now notice here, we've got the units we need. So we've got kilometers, which it states here, and we've got the seconds, which it also states here. Now I have to express this as a compound unit, a speed. So I know that every 3,600 seconds, this object P travels 30 kilometers. So to give it as a speed, we need to think, how far does this object P travel in just 1 second? So it's kilometers per second. Yes? At the moment, we've got kilometers per 3,600 seconds. So it's quite straightforward. We simply divide both sides by 3,600. Okay, let's do that. And I'll write the answer over here. So if you do 30 divided by 3,600, we'll get the final answer, which is, I believe, 1 over 120. Okay, or you can write that as a decimal if you like. I'm just going to keep it as a fraction. equals 1 second. So in other words, the answer is it's 1/120th kilometers per second is the speed. Okay, because every second this object travels 1/120th of a kilometer. And now we can use this answer to work out the next part. So if I take this answer here, it's a short step, isn't it, from changing kilometers per second into meters per second. So all I need to do for the next part is to change my kilometers into meters. So to do that, I've got 1/120, and we know that 1 kilometer is 1,000 meters. So if I multiply that by 1,000, that's going to be in meters, and that's going to equal 1 second. Okay, so we have 1,000 divided by 120. Now, if you do that, you're going to get 8 1/3. Okay, which is meters. It's 8 1/3 meters. Again, you can write it differently if you like. Is equal to 1 second. So the answer for this part is 8 1/3 meters per second. And check your answer makes sense. I mean, if you're traveling at 30 kilometers per hour, you probably traveled at 30 kilometers per hour in a car. How fast does it feel? Does it feel like you're traveling just over 8 meters per second? Okay, does that seem right to you? It's just a sort of an intuitive way of checking the answer. And then for part C in question 1, we're asked to find or state which of A or B is the SI unit for speed. SI, it's actually originally written in French, but it just means the International System of Standard Units. Okay, that have been agreed upon. And the international unit for speed is meters per second. You use meters per second in physics, in a lot of your questions that you do. The velocities are always asked for in meters per second because meters and seconds are also standard units. So the answer for this is B. And I've just noticed that this should be international. Let me just add the AL there. Okay, and then that's question 1 done. Now, for question 2, we're asked to sketch 2 graphs, one y equals f of x, which I've already drawn for you, and f of x is equal to sine x, defined between 0 and 360. And if you'll remember, this is what we call the domain of the function. So from 0 to 360 is the domain. And if you also remember the y values that you get out of it, we call the range. So the range, the y values are range from -1 up to 1 inclusive. And what we're asked to draw here is the graph of g of x, which is sine x with 90 subtracted. So I'm just going to make a note of this, just so we're familiar. So we need to sketch y equals sine of x subtract 90 degrees. Like that. And I've got it written up here, ready to go. So we're going to plot that in a second. So let's just have a look at what's going on. Well, we seem to have a transformation. So we need to think, what does this negative 90 degrees actually tell us? Well, if you remember, it's inside the function. So it's affecting the x direction. And then we have the rule inside opposite. So you'll know from experience that this is going to move the sine x graph 90 degrees that way, to the right. Okay, because it's x subtract 90. So it's a case of drawing it on. Now, if we remember that the sine graph is, unless the domain is restricted, in this case, it's defined for all real numbers. So it will start at -1. I'm going to draw it in green so it matches the label. see if I can draw this accurately. It's going to pass through 90, and it's going to have a maximum at 180, drop down through 270, and then finish at -1 when x equals 360 degrees. Okay, you may notice something interesting about this graph that we've just drawn. It looks a little bit, doesn't it, like the cosine graph, but inverted, if you like. And indeed, you would be right. It's the same as minus cos of x. Okay, just as a little aside there. But generally speaking, you've got one transformation, so it's just one translation to the right by 90 degrees. So in the last question for the warm-up, question 3, we've got a sector, and you'll notice something interesting about this sector. The radius is denoted as r, but the arc length is also r. So if you remember from GCSE, the curved edge opposite the angle at the center is we call the arc length. So in my formula that I've just copied from the definitions above, we know that the arc length L, or you can usually write it as lowercase l, is exactly the same as theta divided by 360, and then you multiply that by 2 pi r. Remember that 2 pi r is the circumference of the circle, and we're taking a small fraction of that circle, literally a fraction, theta over 360, but the 2 pi r is, of course, the circumference. And we're going to use this formula to calculate the value of theta in this case when the arc length is the same as the radius. So this gives us an equation we can solve, believe it or not, even though there'll be 2 unknowns. So let's set it up. So I'm going to do it over here. So we have theta over 360, okay, multiplied by 2 pi r is equal to the arc length, which in this case is r. And now I have to make theta the subject. But before I do that, let's just see if we can, is there any cancellation? Well, we can see that the 2 and the 360 are going to cancel. So this, oops, I didn't want to use that. So the 2 here and the 360 will simplify. So I'm just going to simplify it first. I'll go back to blue as well. So theta over 180. And that should be degrees as well. Multiplied by pi r is equal to r. Okay, let's multiply both sides by 180 degrees. So now we have theta pi r is equal to 180 degrees multiplied by r. Now you'll notice now we've got, and we could have done this earlier, but it's more apparent now, I think. We have r on both sides here. These can cancel. Okay, so we're left with theta multiplied by pi is equal to 180 degrees. It's not the best notation I've ever used here. The pi is a number and it should come before the unknown, but never mind. And then if we divide by pi, we get theta is equal to 180 degrees divided by pi. Okay, which is an angle in degrees, isn't it? So that's the final answer. Now, just think carefully, or just be aware of this. This is going to be important as the lesson unfolds. Okay, and that concludes question 3 and the warm-up. Okay, in our first example, we have to convert 150 degrees to radians. So that's 1a, 150 degrees into radians. Now, if I'm converting from degrees to radians, wouldn't it be great, okay, to figure out what 1 degree is? Okay, if we figure out what 1 degree is equal to in radians, then as a unitary method, we can find out what any angle in degrees is in radians. So we'll focus on that. Now, the way to do that, of course, if I'm going to work on 150 degrees, I'm going to need over here to divide both sides by 180. So let's do that. If I divide both sides by 180 here, 180 the number to scale it down, that means that I'm going to have pi over 180 radians is equal to 1 degree. So let's just write that out explicitly. So in other words, pi divided by 180 radians is equal to 1 degree. That could be another definition for a degree, couldn't it? Yeah. And now we can find out whatever degree we like. So if you're converting from degrees to radians, all you have to do is take your angle in degrees and multiply it by pi over 180. Okay, let's do it. I'll go back to blue, actually. Let's go back to blue. So we take the pi over 180. All right, and we want 150 degrees, so I'll multiply that by 150. And this is radians. And this is equal to 1 degree multiplied by 150. Now, let's see if there's some cancellation here. We need to give our answer in terms of pi where appropriate. Well, it is appropriate in this case. This can simplify down. 150 over 180, that's quite simple. That's going to be 5/6. So the answer, just to finish off, is the following. So we're going to have 5 pi over 6 radians would equal 150 degrees. And let's just see how that looks on a straight line. Of course, let's say we're measuring from the center, a half turn, that's obviously 180 degrees, which we now know is pi, starting at 0. And to get the 150, you simply go 5/6 of the way along, which may be about here. So this angle here, we would now call 5 pi over 6, which is in old money, 150 degrees. Okay, so I hope that was useful. All right, so for part B, I've written out the definition again. Pi radians is equal to 180 degrees. And this time, we're going to find out what 4 pi over 15 radians is equal to in degrees. Now, notice I've got pi radians already, so it will just be a case of scaling. Let's do this. So the first thing we can do is multiply both sides by 4. Let's do that. So I'll multiply both sides by 4. So 4 multiplied by pi radians will be equal to 4 multiplied by 180 degrees. Okay, it's just direct proportion, isn't it? All right, so this means that we've got 4 pi radians on the left and 720 degrees on the right. So yeah, 4 180s, that's going to give you 2 full turns. My pi doesn't look very good there. Okay, now we need 4 pi over 15. So let's take what we've just done and divide both sides by 15. Okay, and this will hopefully reveal the answer. So we can now see that 4 pi over 15 radians is equal to 48 degrees. Okay, and that concludes, that concludes worked example 1. So the next part is an activity for you guys. It's completing a table. So I put in some entries. We've got angles in degrees and radians, so there'll need to be a bit of conversion. And then we've got some trig values, okay? You can use your calculators for this, and I'll leave it to you as an exercise. Can you see if you can complete the table? Okay, so there's enough information there to get you started, and good luck with that. Okay, and then we'll move on to worked example 2 now. So for this worked example, you're asked to sketch trigonometric graphs in radians this time. So you're used to doing this in degrees, and you'll notice the interval that you're given is 0 up to 2 pi. And notice it doesn't say specifically radians. You're going to just have to infer that from the numbers that are used. Obviously, it's in terms of pi. So the question is, what is this interval? And you're going to have to get used to seeing this interval because it's actually a very common one. So what I've done is I've written out the definition again, and we know that pi radians is, of course, 180 degrees. Okay. So the question is, what is 2 pi radians? Well, let's just double both sides of this. So if we 2 multiplied by pi radians is, of course, equal to 2 multiplied by 180 degrees. So 2 multiplied by 180 degrees, which of course is equal to 360. So we've just revealed that this is just a standard interval. We can see that 2 pi, or 2 times pi as I've written here, which is just 2 pi. Let me just change that to 2 pi now we've seen how it's done. So that's just 2 pi, isn't it? Be easier to relate to. So this is 2 pi, and this is just equal to 360 degrees. All right, so once you know those two, you're off and away, really. Let's label our 2 graphs over here. Now, the reason I've drawn 2 graphs is I don't want to do too many steps in one go. We're going to sketch the parent function first of all, and then we're going to sketch the translation, which is required in part A. Now, the parent function, of course, will be y is equal to cosine of x, or cos x, in the interval specified here. Okay, so let's label what we've just discovered. So we know that 2 pi is 360. So let's put that on here. That's 2 pi over here. And we'll do the same for our translation, our transformation, which we're going to do later. And what else do we know? We know that pi radians is 180. Now, 180 is, of course, halfway between 0 and 360. So this is going to be pi. And halfway, just approximately, is going to be pi over there. Now, we need a few more points, don't we? And we can actually infer what these points are without doing any extra conversions. This x-axis now seems to be in multiples of pi. So 0 pi, 1 pi, and 2 pi. So the 90-degree point, which is my first sort of node, if you like, would be halfway between 0 and 1, which is, and in terms of pi, that's going to be a half pi. So I'm going to add that on. This is going to be pi over 2. And again, you're going to see that a lot because that represents 90 degrees. So that's pi over 2, halfway between 0 and 1. And then, of course, we've got halfway between 1 and 2 pi. And halfway between 1 and 2 is, of course, 1.5, or 3 over 2. So we can now write our 270 degrees, which is between 180 and 360, as 3 pi over 2. And on here, 3 pi over 2. So without doing too much extra work, we've got all these vital points, haven't we? And let's sketch the cosine graph first of all. So we'll need the y-axis values on there. They're not going to change at all. So we've got -1 up to 1. And same over here. You've probably anticipated this is going to be a horizontal translation. Well, you should know that. So the range isn't going to change. And let's draw the cosine graph. So let's draw that on there. I'm going to do that in red. So the cosine graph, as you know, begins at 1 and passes through pi over 2. Let's do this as carefully as I can. There's a minimum at pi -1, back up through 3 pi over 2, and then a maximum again at 2 pi 1. So this is y equals cos x, where x is given in radians. Now, on the right-hand side, we're going to sketch the transformation. Now, just to recap, we did one of these earlier. Y equals the cosine of x, cosine of x subtract pi, like that. Now, pi, of course, as you know, is 180 degrees. We know that. And if we're subtracting, this is telling us we're going to have to take my cosine graph and move it in the opposite direction to what you'd anticipate, inside opposite. We'd have to move it pi radians to the right. Now we're in a position to do this. So let's just take some of these vital nodes on the parent function. All right, now the first one, let's have a look at what happens to pi over 2. Well, pi over 2, if I add pi to that, that's going to give me 3 pi over 2. So that node is going to shift to here. We've also got a node, or I'm just saying node as a point of interest, if you like, the point 0, 1, where the maximum is. That's going to shift by pi, so that's now going to be at pi 1, somewhere around here. And then everything else is going to move off screen, isn't it? Now we can draw in our transformation. So I'll do this in green. So we have a maximum here. And then it's going to pass through 3 pi over 2. This means there must be a minimum here at 2 pi negative 1. Yeah, that's moved pi to the right as well. And then another minimum here at negative 0, negative 1. Okay, so this seems to be correct. So this is the graph of y is equal to cosine of x subtract pi. We moved everything pi radians to the right. And just to finish off this question, for part B, we have to state the coordinates of any local maximum or minimum points. Okay, well, on the graph, we've got minima here and here. So I'll just write those down first. So for part B, that was part A, by the way, all that. Just label this as part A and part A over here. So we've got minima at 0, negative 1. And we have another minimum point because we're including 0 and 2 pi. If they weren't included in our domain up here, okay, we wouldn't have to write them in because 0 and 2 pi would not be included. All right, but they are included, so that's going to be 2 pi negative 1. And for the maxima, well, we just have the one maximum point which we found here, okay? So that's going to be one maximum at the point pi 1. Okay, so we've stated those. Then for part C, it asks us to write down the period. Now, the period is how often does the graph repeat itself? Okay. Now, it's a cosine graph. It's been translated by pi radians, but the period won't change. Okay. And cosine has a period of 2 pi, exactly the same as sine. They repeat themselves every 2 pi radians. So we can just say that the period is equal to 2 pi radians. Okay, and that concludes this worked example. So in this next part, we're going to look specifically at trigonometric ratios. And we're going to use the CAST diagram, which you saw in year 1. And we can use the CAST diagram to write down equivalent sine, cosine, and tan values for certain angles. And that applies to radians as well as degrees. So the first thing to notice is on the CAST diagram, let's just put on the angles, but we'll do it in radians instead. So it starts at 0. and make sure I'm annotating correctly. So it starts at 0. Okay, so that's 0 radians. Then we have 90 degrees, which is obviously pi over 2, as we saw in the previous example. Then we have a half turn, which is pi, then 3 pi over 2. And finally back round to 2 pi. Okay, and then you can go around again to 4 pi and 6 pi, etc. And we always measure from 0 anti-clockwise. So this is what we call the positive direction. Okay, let's put this angle theta that we're talking about on the diagram. Now, theta will class as an acute angle in the first quadrant. So I'm going to put that on there. So I've moved theta degrees between the horizontal and the angle. Now, what that means, of course, is that as I move round, I've moved from 0 to the point theta up here. Okay, because I've moved theta degrees from the horizontal. Now, you might say, well, that's obvious, isn't it? But when I draw the next one on, okay, so we're going to draw the next angle in the second quadrant. So let's draw another line like that. Now, this is going to be theta degrees from the horizontal on the negative side. Now, if I move from 0 anti-clockwise, okay, I've not gone a full half turn. I've gone to pi, so I go a half turn to pi, but then I go back by theta degrees. So this value here is pi subtract theta, because we are measuring from the positive let me say that again. We are measuring from 0 in the anti-clockwise direction. So I hope that's clear. This is really important. So notice now this angle that I've written in blue up here is not theta degrees, because we're measuring from 0. Okay, and let's continue in this vein. So we're going to go around to the next quadrant now. So we're going to make an angle of theta degrees with the horizontal. And this time we've gone pi radians round plus an extra theta degrees. Okay, plus an extra. So this must be pi with theta added. Okay, as I continue to move around the cast diagram. Okay, I hope this is okay, guys. Now let's add the final theta in the final quadrant. So we're going to make an angle of theta degrees with the horizontal. And to get to this point, we have done a full turn, but not quite. So we've gone up to 2 pi, but then I'm going to go back by theta. So this must be 2 pi subtract theta. Okay, so those are my angles. So these are really important. We're going to be using these in the next few minutes. So all these angles are going to be really useful. And remember, this is a cast diagram. So we're going to label cast in all 4 quadrants. So I'll do this in green. So we're starting the bottom left. So this is C, A, S, and T, a cast diagram. Now, how does this help us, this diagram? Well, you'll notice the first entry in the table says what happens if we calculate the sine of the angle pi subtract theta. Well, pi subtract theta is this angle here in the sine quadrant, pi subtract theta. And you'll notice that sine in this quadrant is positive. So I'm just going to put a little plus there just to remind me that this is a positive value. So then you use the cast diagram and you say, where else is sine positive? Well, sine is only positive in the all part of the cast diagram. Okay, so that means that the sine of pi subtract theta must be equal to the sine of theta, because that's the angle in the all part of the cast diagram. Okay, that might be a little bit confusing. Let's do another one and I'll show you what I mean. So I'm just going to change colors. This is going to get a little bit messy. So let's have a look at the next angle. This is pi plus theta. So pi plus theta is here. I'm just underlining it now. Okay, now this is in the tan quadrant. Now in the tan quadrant, the value of sine is negative. This is a negative value. So we have to look, where is sine also negative? Well, it's also negative in the cosine quadrant here, but I could write it as a sine of theta if I wanted to. Okay, this is what I want to do. I want to simplify this. It would be equal to sine theta if I just put a negative value in front of it. Okay, so we now know that sine of pi plus theta is equal to negative sine theta. Okay, I hope that makes sense. And then for sine, the final angle we need to consider is the one we just looked at. This is 2 pi subtract theta. Once again, this is negative in this quadrant. Okay, so that means that it would be equal to sine theta, but I'd have to stick a negative in front of it. And you can try this out. Try some acute angles on your calculator and sub them into the left-hand side and the right-hand side of these equivalencies and see if it does actually work. I think you'll find that it will. Okay, let's have a look at the cosine version of this now. So on the cosine version, we've got pi subtract theta. So that's the first quadrant here. Now, cosine is negative here, so I know this is a negative value. Okay, and we can do this a little bit more quickly now. The next one along, cosine of pi plus theta, which is here, cosine is also negative. And the next one, cosine of 2 pi subtract theta, here cosine is positive because it's this angle here. All right, now if we use the same structure, we can see very clearly that if the first one, cosine of pi subtract theta, is negative, then it would be the same as the cosine of theta, but I would have to stick a negative in front of it. All right, the next one, cosine is also negative, so it would be the same as negative cosine of theta. And the final one, cosine is positive. So this is just going to equal cosine of theta. All right, I'm hoping you're seeing the pattern now. All right, and then we can do the tan trig ratios. Let's move on to that. So for tan of pi subtract theta, well, in this quadrant here, okay, tan is negative, so we'll put a negative there. In pi plus theta, this value here, tan is positive. That's the tan quadrant, so we'll put a plus next to that. And in the final one, 2 pi subtract theta, tan is again negative. Notice the pattern. All right. Okay, so to finish this off, these are all going to be equal to tan theta. But we've just got to be a little bit careful, haven't we? Okay, so they're all equal to tan theta, except the two negative values, we're going to have to put a negative in front of them. Okay, now don't worry too much about this. This is just a way of finding equivalent angles. And sometimes you can be asked to convert, for example, a sine of pi subtract theta into something else. And they're quite handy in trig proofs and things like that. All right, but it's just a recap of the cast diagram, and you're getting used to the angles given in radians. For our final worked examples, we're going to find the cosines of some angles given in radians. Now, if this was an exam situation, it would be absolutely fine to use your calculator to do this. But what I want to show you first is how to use the cosines and sines, or the tans, in other cases of angles that we already know, and how we can use the cast diagram to do this. Now, to start off with, you might be thinking, well, I'm a little bit uncomfortable with using radians at the moment, so I'd prefer to be working in degrees, and that is absolutely fine. There's no reason why you can't do that. So what we'll do to make things a little bit more comfortable, we'll change this cosine into degrees. So if you remember from earlier, the definition of a radian, or pi radians, of course, is 180 degrees. So the pi here, I can literally make a straight swap for 180 degrees. So let's do that. So it's going to be 4 multiplied by 180 degrees. And that's what you can do throughout this course. If you see angles given in radians, if you're still feeling a bit uncomfortable, just swap the pi out for 180 and you can get the angle in degrees, no problem. Okay, that's divided by 3, okay, which is the cosine of what will be 720 degrees divided by 3, which is the cosine of 240 degrees. So I've rewritten the question. This is part A, of course. I've rewritten the question as the cosine of 240 degrees. Now, let's draw the cast diagram to see where this lies. Okay, so let's just draw a small cast diagram just here. All right, so remember we start at 0. I can do this in degrees now, that's absolutely fine. So at 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then of course back round to 360 degrees. Okay, and this is a cast diagram, so let's label, let's write on the word cast. So this is going to be cosine, CA, S, and T. Remember, of course, that we measure these angles from 0 anti-clockwise. This is what we call the positive direction. Okay, so the angles are increasing. So we're going from 0 to 90 in the anti-clockwise direction, 90 to 180, and so on and so forth. So where would 240 lie on this diagram? Well, it's slightly more than 180, so, and between 180 and 270. So it's going to go here. So this angle, which I'm just going to draw on here, we know that is 240 degrees, the angle I've labeled in blue, which puts it in the tan quadrant. Okay, so we need to be mindful of that. This is in the tan quadrant here. Okay, now remember from the previous section, we are interested in the acute angle that this makes with the horizontal, that part there. Well, it's 240 degrees. So the difference between 240 and 180 is, of course, 60. Okay, so this is a 60-degree acute angle. This part I've shaded in yellow. This is just 60 degrees. All right. Now, we know from the previous work that I can now put an equivalent angle in the acute section of the diagram. So I'm just going to remove this 240. No, I didn't do that successfully, did I? Just remove that. And let's put an acute angle on here, which is going to measure 60 degrees also. Now then, if we go back to the work we did earlier, we know that the cosine of pi plus theta was equal to the negative cosine of theta. That's from the work you did previously. I can convert this into degrees just by rewriting it as the cosine of 180 degrees plus theta is equal to the negative cosine of theta, like that. Now you'll notice, of course, that what we have substituted in here is the 240, okay? That was the 240. All of that. So that means that theta is, of course, 60. So we've got that theta is 60. So we'll just, again, make a note of that. So theta is equal to 60 degrees. We worked that out from the CAST diagram. And from this identity, we can see it is an identity. I've not written it as an identity, but we'll talk about identities later. This is exactly the same as finding the negative cosine of 60 degrees. Okay? And you can see this from the CAST diagram. If you recall how we set up these diagrams, this angle here, although it's acute, it's not the same as 240. It has the same value as this angle here, although the signs are switched because cosine is negative there and is positive in the all section, the acute section. So that's why I put the negative sign here. Okay, if that's a bit confusing, just rewatch the previous section of the video. So let's write down the final answer. So this is simply going to be, so the cosine of 240 degrees is simply equal to the negative cosine of 60 degrees. Okay, and the cosine of 60 is something you probably know quite well. So this is going to be negative 1/2, which is the final answer. So we've gone from something that looked completely alien to us, this cosine value here in radians, and what we've managed to do is to write it as negative 1/2, which is the negative cos of 60 degrees. Right, now you might be thinking, excuse me, what is the point of all that? Well, it's just to allow you to appreciate how the CAST diagram works and the fact that we can switch between radians and degrees quite easily. All right, I'll show you how to convert from degrees to radians on your calculator in a separate video. Okay, so we'll leave that for now and we'll just write the answer without using the calculator. If we move on to part B, it's a similar story. Okay, so you might want to just rewrite that as the sine of an angle given in degrees. So it's going to be the sine of -7 multiplied by 180 degrees, because we don't want to use, excuse me, we don't want to use the pi radians there. We want to swap it for the 180 degrees. All right, we'll divide that by 6. Okay, and this is going to give us the sine of something else, negative 210 degrees. Okay, so we've got that converted into degrees. Now, again, on a CAST diagram, where will this sit? Well, notice it's negative. Now, if it's negative, if I start at 0 degrees and move in the negative direction, so in other words, this way, clockwise, the first port of call on my diagram would be -90 degrees there. Okay, if I'm going backwards along a number line. I'm then going to end up at negative 180 degrees and then negative 270 degrees. And you go round and round. So this would also correspond to negative 360 degrees as well, the same point on the diagram. The CAST symbols are exactly the same. So this is still C, A, S, and T, and we know what they stand for. So what we do now is we try and locate where is negative 210 on this diagram. All right, well, we start at 0 and we're going in the negative direction. So I'm going to go past negative 90, negative 180. It's going to be somewhere about here. Okay, there it is, negative 210 degrees. And what angle does this make with the horizontal? In other words, what is this angle here? Well, it's just the difference between the two angles. I've gone from negative 180 to negative 210. Now, we've got to be careful here. So let's just find the difference properly. So if we find the difference, we take the bigger angle which is actually negative 180 degrees. And we subtract the smaller angle, which is negative 210. That's what the difference is. It's always the biggest, take away the smallest. So this is going to be negative 180 plus 210. In other words, this is 30 degrees. Okay, that's another familiar angle, so that's good news. So let's put that on our diagram. This is 30 degrees here. Okay, so remember, this is in the sine quadrant. We know that sine is positive here. All right, that's really important. So let's put the acute equivalent on the diagram. So the acute equivalent is going to be here, and it's going to be 30 degrees, like that. Writing out the identity, we know, I'll just write it here, that the sine of this angle, negative 210. And remember, sine is positive in this quadrant. It's really important. This is positive. That means that this sine value is also positive. So it must be identical to just the sine of 30 degrees. Like that. Okay. And then the sine of 30 degrees is, of course, 1/2. So just to finish off, this is equal to 1/2. Okay, and we're done. Now, what I would do is just take these questions with a little bit of a pinch of salt. You are aware that you can use your calculator in the exam, and I'll do a very short extra little video, which will be within the same topic area, just explaining how to convert from degrees to radians and back again on your calculator. Okay, so we'll leave it there for lesson 1.